Let's take a look at some polynomials of higher degrees. A polynomial function, if you remember, is a function of degree n greater than or equal to 0, and it's given by this formula right here. Now, let me just fix this formula actually, because we have x to the first. That should be right there. This formula, the important thing to remember about a polynomial function is that all of the exponents on the variables are greater than or equal to 0. We cannot have negative exponents, we cannot have fractional exponents, we cannot have square root exponents, and we cannot divide a variable with an exponent by another variable with an exponent. Now, the leading coefficient is the number in front of the highest exponential value. So that's got the highest value right there. And the constant term is this guy at the end that technically has an x to the 0 power behind it. But x to the 0, if you remember, equals 1. So we generally write it as just a number. So polynomial functions, we talked about them briefly in the previous section before we went into quadratic functions. Let's now take a look at this definition. F of x be a polynomial function. We say that a real or complex number, x equals c, is a 0 of the function if f of c equals 0. So if we plug in a value into f of x, and when we get through working the value we get 0, it's called a 0 of a function. Now, here are some very important results of this. A polynomial of degree n has at most n zeros. So if you have a third degree polynomial, it has at most 3 zeros. If your polynomial has a highest degree of 12, then it has at most 12 zeros, meaning it has at most 12 times it could hit the x-axis. A real 0 of a polynomial is in fact an x-intercept. So a real 0 will impact the x-axis. Now the thing is that you can have real zeros and you can have complex zeros. So you might have a 0 of x equals 2 where it hits the x-axis, and you may have another 0 of x equals 2i, the imaginary 0, the complex 0. That imaginary 0 will not show up on our x-axis because it exists in the imaginary plane. And we're only interested in the real plane as far as graphing. A complex number, this complex 0, going to part 3, is a 0 of a polynomial, and its conjugate is also a 0 of a polynomial. So complex numbers, if you remember from earlier math classes, complex numbers happen from imaginary numbers, and it happens when you take the square root of a negative number. So the square root of -4, you can't have a square root of a -4. Square roots can only be taken on non-negative numbers. So the square root of -4, what we do is we separate it out to the square root of -1 times 4, and the square root of -1 is then separated into its own square root, and then the square root of -1 is assigned the value I, and that makes it imaginary. And then the square root of 4 is plus or minus 2. So the square root of -4 is equal to plus or minus 2i. That's called an imaginary number because the real world won't let you take the square root of a negative number. Then complex numbers are when you have a real part that goes along with the imaginary part. So, for example, this plus or minus 2i is imaginary. I can make it a complex number by having the real number 0 added to it. Now, I said all of that to talk about this part 3. A plus bi is a 0 of a polynomial, then its conjugate, a minus bi, is also a 0 of the polynomial. What that means is that if I have x equals 2 plus 3i as an answer to my equation that well, when I plug it in, I'll get a 0. Then I also have another 0 that is 2 minus 3i. And when you have this situation where a binomial expression is only different by its sign in the middle, that's called a conjugate. So its conjugate, a minus bi, is also a 0. So let's take a look at example 1. It says, show that x equals 2 is not a solution. However, x equals 1 and also x equals 3 are zeros of the polynomial. Therefore, x equals 1 and x equals 3 are intercepts of f of x. So we're going to go into this, and it has several parts. We're going to start with x equals 2. If we have x equals 2, then we're going to have f of 2, and our polynomial is given right here. So f of 2 is 2 times 2 cubed minus 8 times 2 squared plus 6 times 2. And that works out to 2 times 2 cubed on our calculator minus 8 times 2 squared plus 6 times 2. That's negative 4. For a value to be a 0, when we plug it into our function here, it should equal 0. This does not equal 0, therefore it is not a 0 of the function. Okay, and then it says, show that these other values are zeros. So let's test them. The first value is x equals 1, so f of 1 equals 2 times 1 cubed minus 8 times 1 squared plus 6 times 1, which if we put that into our calculator, we get a value of 0. So this does equal 0. So it's a 0 of the function. X equals 1 is a 0 of f of x. Likewise, our next one to test is going to be x equals 3. So let's test it. F of 3 equals 2 times 3 cubed minus 8 times 3 squared plus 6 times 3 equals 0. Well, I said it equals 0. Let's test it and see what the calculator says. Our calculator agrees. It returns a value of 0. So x equals 3 is a 0 of the function f of x. Now, it goes on, wow, that's crowded, I apologize. It goes on and says, therefore, 1 and 3 are x-intercepts of f of x. So let's check that on our calculator. I have my function entered into my y editor, 2x cubed minus 8x squared plus 6x. And I'm going to hit graph. And it looks like it's intersecting, but I think my graph is not set on standard. Remember, we've talked about that. So let me go into zoom. If your calculator doesn't look like what you expected, go into zoom and hit 6. And that's a much better graph. Notice this function, the highest power was 3. And it happens to intersect the x-axis 1, 2, 3 times. So it has 3 x-intercepts. What that means is that all 3 of its zeros are real numbers. We don't have any of those imaginary or complex numbers happening. Now, if you wanted to verify numerically, you could go into the table. So hit second table. And over here you can see the zeros. When x equals 0, y equals 0. When x equals 1, y equals 0. When x equals 3, y equals 0. So there are the zeros of our functions for that particular problem. Now going on to part B, it says, show that the complex number x equals 1 plus 2i, and therefore x equals 1 minus 2i, are complex zeros of f of x equals x squared minus 2x plus 5. So they are not x-intercepts. Let me take a moment and talk about multiplication of complex numbers, just to remind you. If you remember the first part of this, I gave you the definition that the square root of negative 1 is equal to I. Well, the square root of negative 1 squared, which is I squared is equal to the value -1. And if you look at that statement, that should be what you expected. The square root of -1 cubed, which is I cubed, is equal to -I. And the reason for that is we can take this cubic and we can break it apart into the square root of -1 squared times the square root of -1. Do a little substitution. This guy is I squared, and this one is I. And we just said that I squared is -1. So, I cubed is equal to -I. That's kind of neat. If it's not neat, you could at least say it's convenient. When we start doing our problems, you'll see how nicely it works out. And then the last thing, the square root of -1 to the 4th is I to the 4th, and that works out to the value of 1. The really cool thing about complex numbers, and this is all I'm going to say about it, we're not going to go deep into it, is that when we look at imaginary numbers and you work with them in equations, they're always going to work out to either I, -1, -I, or 1. So I to the 5th starts the process over. It's the same value as I. And I to the 6th is the same value as I squared, which we know is -1. Now we're not going to do much with it. What we really need to know are these first 4 numbers. So let me erase this. So these things are what we need to know for this class. That the square root of -1 is equal to the imaginary number I squared is equal to -1, I cubed is equal to -I, and I to the 4th is equal to 1. Working this problem, you'll see where this comes in. We are to show that this is a complex zero of this quadratic. So, f of 1 plus 2i is equal to 1 plus 2i squared minus 2 times 1 plus 2i plus 5. So I just took the complex zero and plugged it in everywhere there was an x. Now 1 plus 2i squared means we have to multiply itself by itself. So we have 1 plus 2i times 1 plus 2i, and that comes from that squared. Minus, I'm going to go ahead and carry my 2 through. 2 times 1 is minus 2, and -2 times 2i is -4i plus 5. Now, at this point, this is equal to 1 times 1 is 1 squared. 1 times 2i is 2i. Then 2i times 1 is 2i. And then 2i times 2i is 4i squared. I know it's a mess, but let's get some things grouped together now. We have 2i plus 2i, that's 4i, and minus 4i. So these cancel to 0. We have 4i squared, which we've defined I squared is equal to -1. So that means that where I have 4i squared, I actually have 4 times a -1. And then I have minus 2 plus 5. So 1 minus 4 minus 2 plus 5 equals 0. So if I plug that complex number in and use my rules of complex numbers and how they simplify, 1 plus 2i is a 0 of that function. And that means that its conjugate, 1 minus 2i, is also a 0 of that function. And because they're complex zeros, they won't show up on the graph. If we go into our calculator and we decide to graph it, you'll see that this graph is above the x-axis. This is a parabola. It has a positive value for a, so it opens upward. It's never going to turn back around and hit that x-axis. So that means that this function will never have an x-intercept. So it will never have a real 0, which means that since its power is 2, it has no real 0, it must have two complex zeros. And those two complex zeros are 1 plus 2i and 1 minus 2i.